Hello and welcome. My name is Jared Ashton, and with me I have Stefan Chappé. We are both engineers in the floodplain management section at Nebraska Department of Natural Resources, and today we will be introducing you to NFACT. Before we get into it, we just kind of want to give some background info so everyone knows what NFACT is. NFACT is the Nebraska Flood Assessment Calculation Tool. It was designed by Esri with direction and funding from Department of Natural Resources. NFACT is used to perform basic hydrologic and hydraulic calculations. So for hydrologic, it uses the four main Nebraska regression equation sets, Beckman, Kors-Hotchkiss, Singson, and Strom-Admiral, as well as the high permeability regression equations, which were developed for the sandhills by the Army Corps of Engineers. And then for hydraulics, NFACT uses normal depth calculations to determine water surface elevations, and then it can use this to interpolate between cross sections and develop water surface elevation and flood depth rasters and some other things. But these are we use these primarily to develop floodplain boundaries and determine BFEs. So this webinar is going to cover a few things. First off, we'll just cover the basic requirements, software licensing, data required to run the tools. And then after that, we'll be doing a live demonstration of the hydrology and hydraulic workflows. The demonstration will be a brief run-through of the workflow, so there's a more full in-depth workflow available on our FTP site. All right, first off, we'll go over the software requirements. To run the tools, you're going to need to have ArcMap 10.3 and then either 0.0 or 0.1, both work. So you'll need those installed and a license, obviously, to run that. The plan is for Esri to update NFACT to run on newer versions of ArcMap as they're released. So in the future, that should be available, but as of right now, it's designed to run on one of the 10.3 versions. In addition to ArcMap, you're going to need the latest version of ArcHydro installed. There will be a link to the ArcHydro download site later on in this presentation, as well as on the FTP site. Esri has incorporated NFACT into ArcHydro, so downloading and installing the most up-to-date ArcHydro version should guarantee that you have the latest NFACT tools as well. And then finally, you're going to need a spatial analyst license and a 3D analyst license. Spatial analyst is needed for both hydrology and hydraulic tools, and then a 3D analyst is just needed for hydraulics. In addition to the software requirements and licenses, there's some just general background information that NFACT needs. So in order to run hydrology tools, NFACT needs spatial data to calculate all of the regression equation parameters. It'll need contour data, rainfall, soil, permeability, all of that data that goes into the regression equation sets. So Department of Natural Resources has a folder and a geodatabase that contains the majority of this data for the entire state, and these are located on our FTP site in a zip file named NDNR data. And before running the tool, you're going to want to have these downloaded and saved somewhere locally. In addition to the above files, NFACT also requires a Mannings N raster. Like I said, hydraulics uses normal depth calculations, so you obviously need a Mannings N to be able to calculate those. Here are the two download locations. So with that, we'll just kind of jump into our workflow. I will be covering the hydrology workflow, and then Stefan will be covering the hydraulics. So what we're going to find out is a lot of the work to running these tools is in the setup, and then running the actual tools is fairly straightforward. So before we can actually run the hydrology tools, we need to set up a project folder structure. We're going to need to make sure all of our ArcMap settings are correct, and then we'll create a project DEM, and then when all of that is done, we can run the hydrology tools. One second here. So the first thing we're going to do is create a project folder for our project. And it has to be set up in a way that NFACT expects it to. So we're just going to go to our C drive and we're going to create a new folder. You can name it whatever you want as long as there's no special characters or spaces in it. The area we're demoing today is part of the Dog Creek watershed, so we're just going to name our folder Dog Creek. And then after we've made that folder, we're just going to open it up, and then we're going to make another new folder, and we are going to call that Layers. So these folders are what NFACT is going to look for, and it's going to put output data from the hydrology tools, different output data. Some of it will go into the Layers folder, and it'll also create a Geo database called Dog Creek, and it'll put some information in there as well. So after we've created our folder structure, we're going to open up ArcMap, and this will take a second. And we're just going to open a new blank ArcMap document. Okay, so we'll just open a blank one. And before we add any data, we're just going to check a few settings. So the first thing we're going to do is we're going to make sure that our extensions are enabled, so we can just go to Customize Extensions. And like I said, we want to have 3D Analyst and Spatial Analyst. So as long as those are enabled, we're good. So we'll close this. We're also going to make sure we have Geo Processing options set up properly. So if we click Geo Processing, give it a second to load, and then Geo Processing options at the bottom, we want to make sure Enable Background Processing is unchecked. We're going to make sure Overwrite the outputs of Geo Processing options or operations is checked, and we're also going to add results of Geo Processing operations to the display checked. So uncheck background processing, check overwrite, and add results. We'll click OK when those are set. And these geoprocessing settings are saved to your local settings. So if you do that step once, you should be good at least until you upgrade ArcMap. So the last thing we're going to do real fast is we're going to change some ArcHydro parameter settings. So we want to add the ArcHydro toolbar by right-clicking just in the blank space, and turning on the ArcHydro tools. We already have them docked. So once that's open, we're going to go to App Utilities, Additional Utilities, and then Configure Function Parameters. And then under Configuration, we're going to change that from its default to NDNR. And then we'll click OK, and then click Yes. And this just tells ArcMap where to look for the equations for calculating certain parameters. That will have to be done every time you run hydrology. So the next thing we're going to do is create our project DEM. So we will click Add Data, and we're going to navigate to the NDNR, or is that what it's called? Sorry, DNR data folder. One second here as we find it. This is that folder that we're going to have you download off of our FTP site. We're going to open that up. We're going to open up Layers, and we will go to DEM and add that. And this is a just statewide 30-meter DEM. Adding this DEM in first will set the ArcMap coordinates to Nebraska state plane, because that is what the DEM is in. So just so you're aware of that. So now we're just going to, instead of working with a whole statewide one, we're just going to trim it down to our project area. We're going to cheat a little bit here. We have a pre-made drawing that we'll trim it to. We'll zoom to that. So yeah, so once we have just make a shapefile outlining your DEM, and then you can go to Arc Toolbox. Our chat window's in the way. We can go to Arc Toolbox, and then Spatial Analyst Tools, sorry, and then Extraction, and then we're just going to extract by mask. We'll toss in the DEM as our input raster. That shapefile is our feature mask, and we're going to output this to our project folder that we just made. So our Dog Creek, and then here's. and then we'll toss it in the layers folder, and we'll just call it DEM. If you call it DEM, it'll auto-populate some of the later tools. We'll click OK, it'll run that real fast, and then we can just remove the statewide. Here's a quick troubleshooting tip for if you're having trouble running the first few tools in the hydrology toolbox. Just make your DEM larger. It says that in the workflow. It says just make it larger than you think it needs to be. So once we have that, the final step is to click Add Data, and then we're going to navigate to the DNR data. We're going to go to Global Geodatabase and then Layers. We're going to select everything in here and add it, and that's just the layers the tools need to calculate some parameters, and we'll just turn those off when they load so it doesn't slow down our drawing times too much, and hopefully it won't crash right now. But it looks like it might be. Oh, there we go. Okay, so we'll just right click and turn off. Okay, so now our ArcMap should be all set up, so we're just going to go ahead and save this to our project folder. We'll just call it Dog Creek. And we'll save it. Okay, now we can actually start running the hydrology tools. So the first step we're going to do is let's just pin this ARC toolbox so that we don't have to keep expanding it out. Oh, is it? Okay. And we're going to expand the NDNR hydrology toolbox, and then we're going to expand terrain preprocessing, the first tool set, and we'll just click on number 1, terrain processing. This opens up a big dialog box with quite a few things. The first 3 are inputs, so input DEM. If you named your trim DEM, it'll come in pre-populated. Input streams is our NHD flow line, so that's in those that's in those layers that we just added. And then number of cells to define stream. This is kind of an interesting parameter. So what it's asking for is how much area does a drainage path need to drain for the tool to classify it as a stream. So FEMA guidance for regulatory floodplain mapping says a stream must be mapped if it drains over 1 square mile. So it takes 2,877 30-meter DEM cells to represent 1 square mile. So thus our default is 2877. So if you're running a project and you want to consider, a different kind of resolution, so if you want all streams that drain, 0.25 square miles or greater, or if you only want streams that drain 10 square miles or greater, you can adjust this parameter to do that. You just have to do the math and figure out how many cells you need to define that area. So we have 2877. We'll leave that. Everything else is outputs, and we want to leave that as what it defaults to. So we'll just click OK. And this will take a little bit to run. It won't take too long. And this just does a lot of just processing. It'll end up generating hydrology lines, so all of the streams that drain over 2877 cells will be in here. And this can be ran on any size of drainage area. I mean, this one's fairly small. We've ran it on entire watersheds before. It's just a matter of computing power and time. So that one's completed. That took 4 minutes and 3 seconds. We'll close that. And we have quite a few layers that added in. We'll just jump into the second tool, which is create watershed points. Once again, everything in here should be pre-populated as long as you didn't change any names. So we can just run this tool. And this just puts points where streams exit their watersheds. This is just needed for later tools. So we'll close that. That one didn't take long to run at all. So now we can go to the second tool set, which is Hydrology Characteristics. These steps just basically calculate the various parameters for the regression equations. So we'll start out with compute shape-based characteristics. Everything here should be populated, and we'll just run it. This step is just calculating contributing drainage area and compactness ratio for all of the steps, or for all of the watersheds. So we will click close when that's done. We'll just go back to the toolbox again. We'll go to 2.2, compute characteristics by accumulation. The first two are pre-populated, those are right, and the third input global data path, we're going to need to populate that. So we are going to select the layers folder from our DNR data and just add that. And then don't change anything that's checked, and we'll click OK. So this calculates quite a few parameters. If you go back to that, before you actually click run, you can see the whole list of parameters. I won't go through and name them all off because there's like 15. They're all different. They all have abbreviations for the code. When this is done, I can kind of show you kind of the cheat sheet for figuring out what those abbreviations stand for. Okay, so that's done. Kind of what I was talking about there. I can just show you real fast. When you guys open the tools, it probably won't have this tool help. So if you just go to show help, this is kind of good for troubleshooting too if you're not sure what's happening. But if you click in this, just on the scroll bar, it'll tell you all the parameters that are being calculated by this tool. So we just calculated all of those. Some of them you can figure out, a lot of them you won't be able to. So a little like help for that is if you go to If you go to the ARC Hydro Toolbox that we added previously and go to Watershed Processing, Attribute Tools, and go to Compute Local Parameters, this box will pop up, select parameters, and if you expand it to the right, you can see that whole list of parameters, and then it has the actual name or the full name for it, so you don't have to go off of the abbreviation. Okay, and when that's done, since that's done, we'll just keep moving on through the tool. So we'll do 2.3, which is create main flow path, and everything in there should be pre-populated. So we can click OK, run it. This is just calculating the main flow, the main flow path through all of the different watersheds. With the hydrology tools, a lot of them are you're just running it. It uses standardized names from previous tools as inputs for the next tool. So there's not a lot of adding or changing parameters in it. So the hydrology tool ones are fairly straightforward. So when that's done, we'll close it. We'll go back to our toolbox and we'll open up step 2.4, which is compute main flow path characteristics. And we'll run that. While this is running, what this is doing is calculating main channel slope, main channel length, shape factor, and then relative relief. So we'll close that. Go back to Tools, 2.5, Characterize Flow Zones, and we'll run it. This goes and it determines for each watershed which regression equation zone it's in. So for Beckman, you know you have 1, 2, 3, 4, same for chords, and then for Strom and Sinkson, they're differently named, and it just figures out which zone your watersheds are in, so it knows which equations to use in the coming steps. Okay, and that one's done, so we'll close it, go back to our toolbox, and create longest flow path, and we'll click OK. Okay, and it's done, so we'll close it. We're almost done with the second tool set, so we'll open Compute, ADGW, and LFPS using longest flow path. Under Input Global Data Path, we're going to need to select the Layers folder again, and then we'll add that, and we'll click OK and run it. So this is calculating average depth to groundwater and longest flow path slope for the high permeability equations. Right, that's done. We'll go back to the tools. So up to this point, everything has been calculated for the watersheds. So we're going to run step 2.8 here, which just calculates all of those parameters, and it takes them from the watershed and then just adds them to the hydrology lines for those watersheds. So we'll click OK. It'll add everything to that hydrology line that the first two steps created. We'll click Close. And then we can move on to the third toolbox, which is flows. And then the first script there is compute NDNR flows. Under input configuration database, we need to select the global geodatabase from the DNR data folder. We'll add that. And then we will select which regression equations we want to run. We typically just run them all, but if you want to just run one or two, you can do that as well. And we'll click OK. Okay, so that just calculated all of the flows for our various streams. If we go back to the toolbox, there's three other tools under this flows tool set. Snap dam to streams, generate adjustment dams, and adjust flows for dams. So these are separate from the rest of the process. You can quit hydrology at this point if all you wanted was flows for streams. But if you have dams saved in the dam feature class that we brought in earlier, that was in the DNR data, geodata, or the global geodatabase in the layers. If you have dams in there with information that's populated, outflow and points for where the dams are, these steps will snap those dams to your hydrology line and then adjust the hydrology lines downstream of your dams to reflect the dam outflows. So if that's something you have information and you want included in your hydrology, those three tools are available. There's another tool set for interactive analysis. So this is a master tool that runs the hydrology characteristics tools and the NDNR flows tools. So all this tools in tool set 2, it'll run through all of those, and then the first tool in tool set 3. So that's available. We would recommend running through the tools individually. Doing so just allows for review between each step to make sure everything's running properly, as well as easier troubleshooting. So yeah, if a tool fails as you're running them individually, it's a lot easier to figure out what failed than if you're running a master tool. So we would recommend doing each step individually, but there is a master tool available. And then there's one other box that's not numbered. It's just called support, and this just contains a bunch of scripts that the previous tools need to run. You should never have to run these individually, but the tools require these scripts to be in this toolbox in order to run properly. So we've now run through all of the hydrology tools. If we want to open up our hydrology line, if we can find it in this list of folders, and we can open the attribute table. So it created this in the first tool set, and then if we scroll to the right, we can see it calculated all of the parameters, and then we have flows in here. So right now we can see we have sinks in flows calculated. We have no high permeability because it's not in the high permeability region, and then we have strong flows calculated here as well. So that's it for the hydrology tools. I'll hand the mic off to Stefan, and he'll run through the hydraulic workflow now.
So like Jared said, I'm Stefan Chapay, and I'll just kind of run through the hydraulics workflow for us. And we're just going to clean up our map a little bit and delete some of the layers that we don't need going forward. So the only thing we really need to keep in here is that hydrology line that we had the flows for, and we'll just get rid of everything else out of here. Okay, great. That's a lot easier to work with now. So we're going to go into Art Catalog now and make a new folder in Art Catalog where we can work out of our hydraulics. So let's go in that Dog Creek folder that we made previously, and we'll just make a folder in here called hydraulics. Okay, great. And then we're going to open up this folder and we're going to create a new geodatabase. And you can name this whatever you want. We'll just call it Dog Creek again. Okay, and then we're going to open up that geodatabase and we're going to create a new featured data set. We're going to call that Layers. I'm not getting too creative here. And then we're going to pick the state plane for our coordinate system. And then we're not going to set a z-coordinate system. It's not necessary for the tools going forward. And then we're just going to hit Finish. Tolerances we can leave as they are. And then we're going to go into the layers here and we're going to create a couple new feature classes. So the first is going to be our cross-section layer. We'll just call it XSEC. And we're going to make it a line feature type. And then we'll go ahead and hit Next. And we'll leave all the rest as default. Leave those how they are and hit OK. And then we'll repeat that step for our hydraulic line, which is just our stream line that we are going to, or you would digitize, I guess, as the lowest elevation of the stream, or lowest flow path. All right, so we'll finish that up. And then we're going to add those to our map. All right, and then the next thing we're going to add to our map is a LiDAR. If you have it available, the hydraulics tools will work if you don't have LiDAR. Say you just have a 30-meter DEM, you can run everything on that as well. But we have a LiDAR layer that we're just going to bring in. And if you have, you'll notice this is the same boundary we had for our 30-meter DEM. If you do the same step where you do extract by mask in ArcGIS to your LiDAR layer, you can do that as well. But we just took a shortcut and did that before this, so you didn't have to watch it run that tool again. The next thing we want to do is add our Mannings N layer. So we're going to go ahead and find that. Again, this isn't something that DNR provides, so you would have to create this raster on your own if you don't already have one. There's a pretty simple way to do that if you're familiar with GIS at all. You can just create a polygon feature similar to how we just made our cross-section and hydraulic line features, and then you just need a value within that attribute table that is your Mannings N. And then I believe there's a convert feature to raster tool in Arc Toolbox. So we have all the layers now that we need to run the tools. So the next thing we need to do is digitize our cross-section and hydraulic line layers. So I'll show you how to do that real quick if we just go to Edit Features and start editing. And then this pulls up our editor toolbar and we can just click on Create Features. And then we'll select whichever layer we want to digitize in that geodatabase. And we can just draw a cross-section and double-click to finish it. And that's done. So that's just how you digitize features if you're not as familiar with GIS. And again, if you're not, I would recommend just going through the workflow that we provided for you. It's designed a little bit better for people that don't have as much GIS experience. But for this webinar, we're going to focus more on NFACT. So we're going to cheat a little and bring in our own cross-sections. And we'll go ahead and add those. And then you can copy, let's say if you do have cross-sections that you want to use, I would recommend still creating that XSEC layer and then copying your cross-sections into them. So we'll show you how to do that right now. We'll start editing on our cross-section layer actually that we created. We're already editing. So we'll select all of our Dog Creek cross-sections. Just go Selection, Select All. Then we'll hit Copy. And then Paste. And we'll paste it into our XSEC layer. Great. And then we'll do the same thing for our hydraulic line as well. Make sure you unselect your cross-sections before you do this, or you will paste your cross-sections into your hydraulic line as well. Okay, so now I believe we have everything set up. So we'll stop editing and save our edits, and we can get moving with the workflow. So the first thing we need to do is our cross-section and hydraulic line need to have a Hydro ID associated with them. If you have the Arc Hydro Toolbar that we brought in earlier, you can just go to Attribute Tools, Assign Hydro ID, and then if you select the workspace as the geodatabase we just created a bit ago, you can select your cross-section and hydraulic line and then hit OK. and that ran okay. So if you open up the attributes of the exec layer, you'll see it created a new field called Hydro ID, and it populates it with a unique value. The tool needs this to be able to run through the rest of the process. It did the same thing with the hydraulic line, so we'll check that real quick. And again, it has Hydro IDs that are unique. So we should be good to go to start running the tools. So we'll open up ARC Toolbox. And we'll go to NDNR Hydraulics. And again, if you downloaded the latest ARC Hydro, these toolboxes should be brought into your ARC map automatically. If they aren't, you can look at the workflow and it specifies the location where you can find them. Okay, so in step 0, data preparation, this is a standalone tool that is not part of the remaining workflow. It's used to transfer the attributes of the hydrology line created in the hydrology toolbox workflow into the digitized hydraulic line. So the hydraulic line can then be used in the AH profile toolbar. This is a tool that can be used to check that flows are increasing as you go downstream. So again, you can look and you see that AH profile tool set. That's kind of a quality check tool that you can use. Let's see. The only downfall, or you can use that tool or that toolbar without running that tool. You'll have to use the hydrology line as the input, and the only downfall to that is that the riverbed profile that it displays isn't as accurate as your digitized hydraulic line would be. Okay, so we'll move on to step 1, and we have a couple options for getting started. Step 00 is the most common, and we will use it since we have a hydrology line that was directly output from the hydrology toolbox. So we'll open that up and we'll put in our cross-section layer that we just created, as well as our hydrology line. And then we'll save this output in that Geo database that we created, Dog Creek, hydraulics, and then within that layers data set, we're going to just call this exec2D, and we'll go ahead and run that. So what this tool does is it transfers the attributes from the hydrology line to the cross-section layer. You'll notice throughout the process that some of the tools create new output features while others simply update the input feature. This particular tool creates a new output cross-section, so we'll use that one going forward. And alternatively to step 00, you can run step 00A. If you don't have a hydrology line and instead you have cross-section features that you have flows associated with, in order for the workflow to work correctly, with this tool you'll have to have the attribute fields named STQ10, ST_Q50, and so on for the Strom regressions. And the workflow also lists the prefixes needed for this tool to run correctly, if that is something you would like to do. Okay, so we ran step 00, so we don't need to run step 00A. So we'll move on to step 1. And for this, we'll input our exec2D layer that we just ran, as well as our hydraulic line that we would have digitized. And then for our elevation surface, we're going to select our LiDAR layer, and then we'll select an output. We're going to call this hydraulic line split. So the tool splits the hydraulic line at any location where there is a cross-section and then calculates the slope for each of those segments. There are several slopes calculated in the attribute of the output feature, and you can see the workflow to see what those all are. The slope used going forward will be using the attribute SLP for slope, and that's calculated by subtracting the elevation of the most upstream point of the segment from the most downstream value and then dividing by the shape length. So this is a good point to have a check to make sure your slopes are positive. So we'll go ahead and open up the attribute table of our hydraulic line split, and you can see our SLP field, everything is looking positive, so it doesn't look like there's any manual edits that we'll need to be fixing right now. However, if you're running this on a much larger scale, there's greater likelihood obviously that you could run into that. But we can go ahead and move forward to step 2. And for this, we'll put our exec2D layer again, and then we're going to input our hydraulic line split layer that we just created, and go ahead and hit run. So the tool assigns a slope value to the cross-section layer in the attribute S0. So if you open up XSEC 2D, we now have a new field S0 at the very end, I believe. Yep. And those are all positive, so that looks good. This slope is calculated by using a weighted average of the segment on either side of the cross-section. So again, this is just another good point to check that your slopes are positive in your cross-section layer, especially if you didn't check it in the previous step. Okay, so we can move on to step 3. This one's pretty self-explanatory. It's just calculating Mannings N for your cross-sections. So we're going to input our XSEC 2D again, and then our NLCD Manning layer. And go ahead and hit run. The tool is calculating the Mannings N attribute, and that's determined based on the mean N value for that cross-section. Also, this tool is one that is just updating that XSEC 2D layer. So you'll see if we open up that attribute table again, there's just a Manning N field that has been added to it. Okay, so with that, we can go ahead and move on to step 4. And for this, we're going to input our XSEC 2D layer again, as well as our LiDAR layer. And then we're going to name our output XSEC 3D. And again, we're saving everything just in that same data set that we created at the start. And we'll go ahead and hit OK. So what this tool is doing is it's converting the cross-section layer, that XSEC 2D, into a 3D line feature using that input raster, which for our case was our LiDAR. And you'll see the output XSEC 3D layer has multiple points that each has an associated elevation. So if you start editing on that XSEC 3D layer, and maybe turn off some of these other ones so we don't get confused, and then we double click on it, you'll see there are a ton of points on those cross-section lines, and each of those points has an associated elevation to it. So that's what our 3D cross-section layer is. We can go ahead and stop editing. And we can jump into step 5. So this tool will by far take the longest of any of them to process. Typically, if we're running this on a HUC 8 watershed basis, we'll designate a computer for it and have it run overnight, just because it can take quite a bit of time. The tool is an iterative process to determine the hydraulic parameters for each cross-section for various slicing measures. The time it takes is all dependent on your inputs, so I'm going to fill out my inputs quick, and then while it's running I'll explain what they are. Let's see. So let's use a slicing type. We'll leave those as default. And everything else we're going to leave as is. So we just input the XSEC 3D, and we'll go ahead and hit OK. Okay, so the first input was that XSEC 3D layer that we created in step 4. The more cross-sections you have, obviously the longer this step is going to take. The second option we had was to define how the tool is slicing cross-sections based on slicing type and slicing measure. Slicing type 1 is slicing type 1, which is the default, and what we chose uses a constant slice height designated in the slicing measure. The default value for that is 1 foot, which is what we used. Another way of thinking about it is having 1 foot of water flooding the cross-section and having parameters such as wetted perimeter, hydraulic radius, area, all calculated for that specific depth. The process then repeats for 2 foot, 3 foot, etc. The other option you have is to choose a slicing type 0, which produces a fixed amount of slices for every cross-section. We typically don't use this option simply because the margin of error is inconsistent between varying sized cross-sections. Deep cross-sections will have a larger potential for error, while shallower cross-sections are likely being analyzed to an unnecessary degree of preciseness. So if you have a set of cross-sections with similar depths, this tool, or slicing type 0, can actually be pretty useful and run a little bit quicker, most likely. Another option we had in the tool is to set the maximum depth to be iterated if we're using that constant height method. Be careful in using this option, just because if the normal depth calculations conducted later in the workflow are calculating depths greater than that H value that you specified, you're going to have erroneous water surface elevations. So this is a fairly new option to the tool, I think only about a week old, just to help us with reducing the time it takes to run this step. So I don't actually think it's in the workflow that we sent out. However, if you do go to the FTP site, it has been updated in that workflow. So there's just a short description on what that H value is. So the main output that we're going to see from this tool is a table. It's going to be PF underscore and then whatever your input cross-section layer was. So ours will be PF underscore XX3D. What it has is it contains parameters for every iteration for each cross-section. So it's a pretty big table. The XID in the table relates to the Hydro ID of the XX3D layer. So if you need to figure out what's going on with a specific cross-section, you can link the two. Another option that was in the tool was to append results. You would only need to consider this option if you're running the tool over again. If you are, you can select option 0 to overwrite the previous table that was created. And the alternative is option 1, which allows you to add results to the table. This can be useful if you have added cross-sections to your XX3D layer and you want to run step 5 only for the added cross-sections instead of running the whole tool all over again, essentially. So in summary, the main output from this tool is the PF table that has the hydraulic parameters calculated for each regression. You'll notice in this processing bar that it's giving you a little bit of detail. So it says XID 91, 9 of 14 processed. So 9 out of the 14 cross-sections have processed at this one I'm highlighting here. Also, it has 517 records added. That means there's 517 records added to that PF table that we're creating up to this point. So for this one, for this particular cross-section, if you take 517 minus your 465, that would be how many records were total added for that specific cross-section, which I'm being told is 52. That sounds about right. Another thing to make sure everything is running smoothly before you get started, I should have mentioned this when we were getting stuff set up, but your cross-section lines will need to be crossing the hydraulic line as well as the hydrology line exactly once. Otherwise, you will get errors. I'm not sure at what step you would get those errors, but eventually sometime down the line you will. And that can be a pain, especially if you've run through this step and then you can't get your water surface elevations to calculate. So just be sure you're checking all of your input data at the very start before starting on that step 1. But we're on our last cross-section. It's processing, so it should be done here shortly. Oh, there we go. Right on cue. Okay, so we'll go ahead and close this. Okay, so now we can look at that table that we just created, and you can see we have some of those hydraulic parameters calculated in here. Again, here's that XID field that I referenced you to a little bit earlier. This is the link to the Hydro ID of the XX3D layer. So you can see there's a bunch that have that same ID. That's because they are different iterations for that same cross-section. You can see the deepest one was 60 feet. And then, let's see. Yeah, so this is just one cross-section and then all the iterations it has. So 60 feet all the way down to a foot in depth. So you have your depth, you have your area, you have your wetted perimeter, hydraulic radius, and your width. Okay, so I think we can move on from there finally, and we can jump into step 6, which is calculate potential Q. And we're just going to input our XX3D layer as well as that table that we just created. Unfortunately, you can't drag and drop tables in GIS, which is annoying, so you'll have to click the drop down for that. And then we'll go ahead and hit OK. This step is taking the hydraulic parameters in the table that was created and then calculating a Q value for each depth of flooding. So that Q value is added to that PF table. So if we open that up again, you'll see simply we just added that Q value in that table. And then we can jump into the next tool, finalize cross-section attribution. And again, we'll use the same inputs, and we'll use the drop-down to find the table, and we'll hit OK. So this tool updates the PF table once again just to include a slope as well as the Mannings N fields. This is done simply so that it's easier to hand calculate Q values in that table using the Mannings equation so that you can compare the values just to make sure everything is calculating right up to this point. So again, that tool is just adding attributes to that PF table. We can move on to the next one, which is step 8. And this is finally using those iterations from that PF table to calculate the flood depths and elevations for each regression and frequency. So we'll input our same inputs that we have been, and we'll go ahead and hit OK. So the tool uses 2 iterations from the PF table that result in Q values on either side of the actual Q in that XX 3D layer. So if your actual Q is 100,000 and you only, let's say you had really high iteration values, so you had a 200,000 and a 50,000, it's iterating between those two to find out what the parameters should be for that specific cross-section. So the depth and elevation are then calculated based on the interpolation between the 2 iterations in the PF table. The XX 3D layer is updated to include depths, elevations for each regression and frequency, and those are noted by the H and Z fields if we open that up. So we can scroll all the way to the right here, and you'll see we have, so for Sanction we have SO_H25. So for each cross-section we have a depth for the Sanction 25-year frequency, and so forth. We have those for each of them. Let's see. So step 5 and step 8 are your main tools for calculating water surface elevations. The rest of the tools are essentially setup steps and cleanup steps. So if you're having issues with elevations not looking right or something not going right with those, 5 and 8 are the outputs from 5 and 8 are the places to look. If that's all looking okay, we'll move on to step 9. And we'll input our XX 3D layer, and then we'll also choose what regression we want to use. So we're going to use Strom for this, so we'll select ST, and we'll go ahead and hit run. This tool simply creates a Q2, Q5, Q10, etc., as well as a WSE2, WSE5, WSE10 attributes, and then it copies the values from the selected regression into those fields. So if we open up that table, I'll show you what I'm talking about. So now instead of having the weird just ST_H500, etc., we have just, or Z, I should say. It copies that Z value into your WSE fields, as well as copying your ST_Q values just into a Q100, Q10, and all of those. So this just makes the data look a little cleaner. Yeah, and that's essentially what the next step is doing as well. This next step is optional. It just kind of cleans up the data a little bit. So you'll notice by now we've generated quite a few fields in that XX 3D layer. It's quite the layer. So this tool simply reduces those attributes. So it'll create a new feature with the fields sorted in a more logical way, and then it also hides some of the fields that you might not need most of the time. They don't disappear, so if you need to add the attributes back in, you can go into the into its properties and add those fields. So we'll go ahead and hit run. We'll save these first. So again, saving everything to that same layers data set that we created, and we'll name this first one XX 3D sort, just because this is the sorted cross-section layer, and then we'll leave that next one just how it is, and we'll hit run. And that completed, and we'll look at the outputs real quick. So this first one, XX 3D sort, you'll see it has all of the attributes still. They're just in a different order now. And there we go. So it has all of our hydrology parameters more towards the end, and our water surface elevations at the start. So we'll close that, and then we'll open up that view. And this is actually the same layer as the other one, so if you look in ARC catalog you won't see two different layers, you'll just see one. But here you can see it only has a select number of fields. So it has your Q values and your water surface elevation values, which are the big thing. So we'll jump into the floodplain delineation tools. Let's see. So for these you're going to want to run either step 11 or steps 12 and 13. I realize that's kind of confusing. That's just how it's set up, unfortunately. So 11 is a tool you can run on your own, and if you're familiar with ARC Hydro, you might have seen that tool before. The new tool that is specific to NFACT is the steps 12 and 13. So for step 11, this is an option to delineate a floodplain, and what it does is it's generating a water surface elevation raster without any regard to the input cross-sections connectivity, essentially. So all it sees is your cross-sections. So we'll just skip that tool for now, and we'll jump into step 12. So this is the setup tool for running the flood from cross-section per reach tool. The tool associates the cross-sections with the input reach and then sorts them based on an attribute within the cross-section layer. For our case, we're going to use the water surface elevation. This makes the check we did following step 9, if you'll remember, to make sure that our water surface elevations are decreasing as we go downstream. I'm not sure if I mentioned that before, but after step 9, where you have your WSE fields calculated, you will want to make sure that your elevations are making sense and that they're decreasing as you go downstream. So apologize for not including that previously. But again, we're going to use those water surface elevations as sort of a sorting field for what is more upstream versus downstream in our cross sections. So it is important to have that check. Another option is to generate a stream station attribute and use that as your sorting field instead of your water surface elevations. We did not include that as part of a workflow, so you would have to have some way of calculating that stream station on your own. The input river corresponds to the hydrology line for our case because we started at step 00 as opposed to that step 00A where you would use your hydraulic line. Yeah, so we'll go ahead and put our inputs. So our XSEC3D, our upstream sort field, we're going to use our WSE 100 because that's what we're going to be using to delineate. And then we're going to input that hydrology line. And then this also creates a new cross-section layer. So we're just going to call it XSEC3D reach. So we know it's by reach. And we don't want any special characters in here, so we'll get rid of that. That is one thing that can cause the tool to have errors, and they're not necessarily errors that pop up in GIS that are very useful. So make sure all of your naming conventions don't have any special characters. Underscores are the only exception to that. So you can see here it's processing 8 cross-sections for one of the reaches, 9 for another, I believe. Oh wait, sorry, 2, 6, and 0 on one of them, and then 2. So that 0 cross-sections, it's just referring to that very downstream reach where we don't have anything down there. So we'll go ahead and hit close. And then we're going to jump into step 13 to actually delineate the floodplain. So this tool delineates a floodplain based on a reach-by-reach basis. All cross-sections on a particular reach as well as the first cross-section on the next downstream reach are used to create the water surface elevation raster. So the tool allows for an option as to where the raster boundaries overlap. We typically use the maximum option to choose the higher of the 2 overlapping water surface rasters. Some of the other options may make the boundary at confluences look cleaner, but it's more difficult to discern what the correct boundary should look like when you're using something such as blend or mean. So again, we'll use the hydrology line as our river input because we have associated hydro IDs in there. And if you see the tool help on the right, it kind of explains what you need for your hydrology line if you click on that. There we go. So it specifies that you need that hydro ID as well as your next down ID, I believe. Another option we have in this tool is to limit the extent of the flooding to either the river or an input boundary. So if you click on the Apply River Restriction, that'll reduce the floodplain just to areas that are touching the river. And similarly, if you input a floodplain, it'll limit your output boundary to be inside whatever that polygon feature you've added is. We typically don't use this except in some cases when we have a 500-year boundary already developed and we're running a 100-year boundary delineation. That way we ensure that our 100-year boundary is within the limits of our 500-year boundary. So we can go ahead and hit run on this. Sorry, I got to specify some other outputs first. So our results folder, let's go back into that hydraulics folder that we created at the start. And we'll hit add. And then we're going to add a short process name. This just creates a folder within the folder we just selected. So we're just going to call this Proc 100. And actually I will make a note that this says up to 10 characters. It is actually less than 10 characters. So if you have 10 characters, this process will fail. So just be wary of that. We'll go ahead and hit OK. Okay, and that finished running. So it'll spit out quite a few things in your ArcMap, so we'll start looking at those. On top you can see your floodplain boundary, which is that FP Poly Proc 100. And we'll zoom into the confluence here. You can kind of see how this tool differs from just the flood from cross-section is where you have the overlapping tins. You have a little bit different boundary where they're coming together. You can see that it jets out a little bit right there. But otherwise it looks pretty good, so we'll go ahead and turn that off. And then we have the water surface elevation, or unrestricted water surface elevation Proc 100, and that's what you're seeing right now is that extended boundary. And we'll go ahead and turn that off. And then we also have our WSE Proc 100, which is the same thing as the unrestricted water surface elevation. It's just clipped to the boundary that was created. And then lastly we have the flood depth raster, and that's just the water surface tin that's clipped to the boundary and then subtracting out the LiDAR data that was underneath. So that's what that tool is giving you. And from there we can jump into our BFE derivation tools. First what we have in here is a derived BFE no smoothing, and what that's doing is just adding the depth raster to the ground raster and then running the contour tool from Arc Toolbox to generate BFE lines. The next tool we have is similar. It's the derived BFE with smoothing, and what that's doing is the same thing as the above tool, except it's going to smooth the edge of your water surface elevation tin, so you have a little bit cleaner boundary that the BFE lines are extending to. And next we have the derived extended BFE by specified distance from river. So we'll open that up. It's a little more complicated. So for the inputs you'll use your water surface elevation raster again, and you'll also input your hydraulic line. And what the tool is going to do with that is it's going to buffer it a specified distance that you can see there next. It defaults to 100 feet. And then it's going to use the contour tool again, but it's going to clip your BFE lines to that buffer that was created. So if you're using 100 feet as your buffer, your BFE lines are going to be 200 feet in total length. This tool is good for doing a lot of manual edits. If you have an area where maybe you have cross sections that are a little bit strange, or you're near confluences, this tool can help because it makes the BFE lines really small, so there's a limited amount of error that you can see in those. Unfortunately, then you have to do a lot more manual work in extending those BFE lines to the boundary if that's your final output that you're wanting to see. The next tool we have is the derived extended BFE by specified polygons. This is the one that we use the most, and we'll run that for you. So what it's going to do is it's going to create BFE lines using our water surface elevation tin and extend them and clip them to the input polygon. So we'll use our floodplain polygon that we just created, and then we'll input our unrestricted water surface elevation raster that was also created. We're going to use the default input of 1 foot. That's going to be a 1 foot spacing between each of your BFE lines. and then we're going to output our BFE line into the same geodatabase we've been working in and call it BFE, and then we're going to hit OK. And we'll close this, and you can see it generated BFEs, and if we turn on our boundary, you'll see that it's clipped to those. So in general, it's doing a pretty good job. You can see near the confluence, there's just those weird things going on where the two water surface elevation tins meet. And then if we start editing on that line, I'll show you why we have the tools we do after this step. So we'll zoom into one, and you can see there's a ton of vertices here on all of our BFE lines. So what the next tool is going to do is reduce the amount of vertices on your BFE line. So it's going to just be the endpoints of the BFE and this center line, which is the river. So this is our generalized BFE using 3-point method. So we'll input the BFE lines that we just created. We'll input our hydraulic stream. You can use your hydrology stream as well, but the hydraulic line generally is a better, or should be a better line for better representing the stream bed. And then we'll name this BFE Gen just because it's the generalized BFE line. Okay, so we'll go ahead and close this, and if we start editing on the new lines that we created, you'll be able to see that now there's only 3 points on our line, which makes it a lot easier for editing. The next tool is similar to this one. It is generalized BFE using multi-point method, and this one differs in the fact that if you have a BFE line that is crossing multiple hydraulic lines, or crossing a hydraulic line more than once, it'll leave all of those vertices that are crossing. So you'll have 2 endpoints and then however many other vertices there are that cross the hydraulic line. The 3-point method just chooses one, I believe randomly. So if you have that instance a lot, you might want to use the multi-point method tool and manually decide what you would like to keep. The final tool we have is our Refine BFE tool. And this just adds one more step to our BFE lines to finalize them. So we'll input that BFE generalized and then our hydraulic line, and we'll name our output BFE BFE Ref for BFE Refined. And what this tool is doing is creating a new field in its attribute table that I'll show you real quick. And it's called Odd Even. This is useful in case we have BFE lines that are stacked pretty close on top of each other. We can select all the even numbered BFE lines and delete them out. So essentially increasing our contour spacing to 2 feet if we didn't know that was going to be the case going in. Otherwise we can edit the inputs to the tool. Either way works. The other thing that this tool does is it deletes BFE lines that are not in contact with the hydraulic line. So if you look at our BFE generalized here, there's a few extra lines that aren't crossing. They're just kind of erroneous. So it cleans those up a bit. And so that's it for our BFE derivation tools. The next on the list is our automation tools. We have a few of them here. So the first one is the characterization master process from hydrology. So that runs all of the steps in toolbox 1 from step 0 to step 10, not including step 00A. Step 00A characterization master process auto from hydraulics is the exact same tool, except it starts off with using step 00A instead of step 00. We also have the floodplain delineation master tool, and that simply combines steps 12 and 13 of the floodplain delineation tools. 12 again was just that preparation step for step 13. We also have the BFE derivation master process. This one combines all of the tools that we just ran through for you. So the derive extended BFE by specified polygons, the generalized BFE using 3-point method, as well as the refine BFE tool. And lastly, we have the flood from unrestricted water surface elevation raster per reach. So this tool can be used if you, for some reason, already have water surface elevation rasters, but you do not have a specified boundary. you can input all of your water surface elevation boundaries and it'll give you a floodplain boundary in the end. So that's all we have for the hydraulics toolbox. Just a quick warning again against using the automation tools. I would refrain from using them, especially at first, because it's difficult to know what errors you're running into if you are running into errors. There's also limited availability to have any quality checks along the way. For example, we checked the slope, we checked the elevations increasing or decreasing rather as you're going downstream. So there's just limited ability to QA the project as you're going along. So just a quick disclaimer for you here at the end. NFACT was designed by Esri with direction and funding from NEDNR. NFACT is a tool for performing basic hydrologic analysis using Nebraska regression equations and basic hydraulic analysis using normal depth equations. Esri has designed the tool to be integrated with their ARC Hydro tools, and NEDNR is providing the tool to the public for their use. However, NEDNR does not have the funding or authority to provide technical assistance or troubleshooting for this tool. So the majority of the webinar we focused on the workflow for hydrology, which Jared covered. This included the necessary setup steps as well as the actual workflow of the toolboxes. Lastly, I covered the setup and workflow for hydraulics, which included 3 parts. That was the hydraulic characterization, where we calculated the water surface elevations. And then we had the floodplain delineation and BFE derivation steps. The webinar was intended to cover the essentials of NFACT. It didn't cover in as much detail the setup steps that were required in GIS. If you're less familiar with GIS, you can use the step-by-step workflow, which was written to help those who might be less familiar. Thanks for listening to this webinar on NFACT, and happy mapping.